Hello everyone, my name is Emily Centamore and I have been working through the Randall Research Scholars Program under Dr. Sergei Gleyzer in the Department of Physics and Astronomy. I've been working on computational analysis for the identification of exotic Higgs decays. In this presentation, I'm going to give you a little bit of background on particle and collider physics, some information on what the Higgs boson is and what decay I'm looking at, and then the method and results that I have so far and the future work. So what is particle physics? Particle physics is the field of science that attempts to understand the most foundational particles in the universe and their interactions. The biggest accomplishment from this field is the Standard Model, which is a mathematical description of all of these particles and their interactions. You might see on the visual on the slide some familiar particles like the electron or the purple quarks, but there are many more that comprise the universe that we know. However, the Standard Model is not a complete representation of everything that comprises the universe. We do not know how to explain things like dark matter, for example, and these are things that are ongoing efforts in the scientific community. Now, the Standard Model is not purely based on mathematics. It is also based on experimental confirmation, which brings us to the field of collider physics. The biggest center for collider physics is the largest particle accelerator in the world, called the Large Hadron Collider, or the LHC. This is a approximately 17-mile-long collider, and it accelerates particles to over 99% of the speed of light. One of the detectors on this collider is called the compact muon solenoid, and it is a multi-layered particle detector that detects the energy, momentum, and tracks of particles as they travel through its layers. Now, the data from the detector can be put together to create reconstructed images of collisions that look something like this. You can see in the middle of the detector, the center of the collision, the orange tracks as the particles expand outward, and the energy deposits on the edges of the calorimeter in orange, green, and blue. As I mentioned, collider data is used to confirm the Standard Model, but it is also used to explore theories that would expand the Standard Model to be a more complete representation of our universe. The most recent discovery from collider physics is the Higgs boson, which was discovered in 2012 and is the newest particle that we know about. However, a lot of its properties were unexpected. They didn't match up with a theory that we had, and because it was discovered so recently, it is pretty unexplored. So that means it has a lot of potential for revealing new physics that we can find. And it is around this particle that my work centers. So the decay that I'm looking at is the decay of the Higgs boson into two pseudoscalar particles, A, which then decay one into two photons and one into two gluons. You can see the visual on the slide, but I'll also verbally walk through it a little bit. So the Higgs boson first decays into two identical pseudoscalars. These are the same particle, A. One of them decays into two photons on the top, and the other into two gluons on the bottom. The Higgs boson, the photon, and the gluon all currently exist in the Standard Model, but the pseudoscalar A would be evidence of new physics. Now, it is important that the decay that I'm looking at is able to exist within the existing constraints of the Standard Model and of experimental results. There are lots of theories that allow these beyond Standard Model decays, but the one that this one occurs in is the two Higgs doublet model plus scalar. This model theorizes the existence of a second Higgs boson, which would be indistinguishable from the one that we know of in the detector, but its existence also allows the existence of a second new particle, a scalar or a pseudoscalar. This new particle would still fall in the same category as the Higgs boson in the yellow column under scalar bosons, but it would be distinguishable from the Higgs in the detector. Again, the key takeaway here is that this model and the decays that result from it do not conflict with the existing results that we have. To get a little bit into the method of analysis, we employ two major techniques, data generation and machine learning. So the reason that we use simulated data is so that we can verify the results that we get using the data that we employ. With collider data that is collected organically, you cannot know what is originally happening in the detector. That's the purpose of the detector. So you only have the readout results. But with the simulated data, we can ensure that the data that comes from completely inside the collider and the data that comes from the detector readout are the same, or if they're not, we know the difference. Second, we employ machine learning, which addresses two specific issues with the data we collect. One is signal merging, which if you see in the visual on the slide, it appears to be two tracks going through layers of the detector. Those are the yellow stripes. But sometimes particles travel so quickly that those tracks kind of merge and appear to be just one track, and it can be difficult to distinguish when one particle is going through that detector or two. Machine learning is better at identifying the difference between single particles and merged double particles, so that is one implementation that is helpful for. Second is there are high levels of background. So in the Higgs decay that I'm looking at, the results are photons and gluons. However, there are lots of other decays that are more common that have these same results, and it can be difficult to tell the difference between the signal, the Higgs decay, and the background, any other decay that we don't find as interesting. So the implementation of machine learning here can also help us tell the difference more efficiently. So the idea is to use the simulated data to create a model that would work when applied to real collider data. To show you a little bit of what I've done so far, here are some outputs of the simulated data. So you can see in figure 1 on the left, this is the mass distribution for the photon-producing pseudoscalar. You can see it's limited to right about 2.5, and it is more frequently occurring at those higher mass levels. And in figure 2, you can see what the detector reads out as the mass distribution of the photon-producing pseudoscalar. So you can see that it peaks right around that maximum mass value, 2.5, but the detector actually reads as finding mass that is above what the maximum limit is in the initial generation phase. On this slide, in figure 3, you can actually see a direct comparison between these two distributions. On the x-axis is the generated pseudoscalar mass, and on the y-axis is the detector readout of the pseudoscalar mass for the photon-producing pseudoscalar. You can see there's a pretty strong diagonal correlation, so they look very similar a lot of the time, but especially above the diagonal, there is a little bit of extra, which is where the detector estimates the mass to be higher than what it actually is. And in figure 4, this is a comparison between the initial mass of the photon-producing pseudoscalar on the x-axis, and on the y-axis, the gluon-producing pseudoscalar. You can see that that's a perfect diagonal correlation because I required that the two pseudoscalars were identical. So future work for this looks like first doing a mass regression to determine the mass of the pseudoscalars. So we're using results from the end products to backtrack and figure out what the mass of the pseudoscalar is most likely to be. Second is trigger studies. When data is collected in the collider, it is filtered to see what is most likely to be interesting and what is most likely not to be, because not all of the data can be stored. So this is looking at the categories of data that are actually collected in the real data and seeing if my decay is likely to occur in it. Finally, there will be the development of that classification model, which will be to distinguish between the interesting Higgs decay and the not so interesting background decays. Thank you very much. Do you have any questions?
So can you give us like an appreciation of the size of the data set? And are there multiple instances of the data set, or is it too expensive to do this? There's only like one data set out there. So just curious, like the size, and then how many data sets can you access?
Yes, so when I'm using simulated data sets, that's very controllable for how large that is. So the samples that I displayed here, there were about 100,000 instances generated, but generally they would tend to be in more of like a couple million would be the scale. And I'm not entirely sure what the size is of the actual data sets we would look at, but the detector collects data at a very high rate, and looking into those trigger studies would also give a better idea of what I'm looking at.
You talked a lot about a pseudoscalar particle, 2 of them, as part of your decay. Why not go directly from Higgs to the gluons and photons instead of needing to add this new particle?
Yeah, so the introduction of the pseudoscalar does give an avenue for discovering new physics, because that's the key part that would expand the standard model. And then also, direct decays from the Higgs to the gluons and photons requires an intermediate process because of the properties of the particle interactions. So it gives a little bit of a higher probability to look at decay through those pseudoscalars.
There was a part you mentioned about the indistinguishability of one of the like secondary particle. I didn't really catch all that. Can you explain that again? 5 or 6, you were saying, where'd it go? Oh. You said that there was a part that, a second particle you couldn't, it was indistinguishable.
Was
and I
it?
wasn't sure. I understood. I just, can you say a little more about how that happens, or?
Do you mean like when the signals become merged and look like one or two?
Yeah, that part.
Okay. So basically, when you have very light particles, because photons and gluons are massless, they travel so quickly that they can hit the detector very close together, and so being able to distinguish between those two tracks is limited by the resolution of the detector. So that's where you kind of get that merging of signals.
Yeah, so you had a graph that showed the error of the detector towards the end when it was reconstructing the mass of the pseudoscalar. Is there any way to improve the accuracy on that?
Yes, a little bit. So at the raw base level, that is limited by the resolution of the detector, so how well it can distinguish exactly what the energy is. But there are ways to improve that with machine learning, because when the detector is doing readout here, it's looking at a collection of data, but machine learning might take information from other less direct indications that would give a better readout.